Welcome back, engineers. In this video, we're going to go down history lane. We're going to see how API communication has evolved over the years. We'll try to understand the pros and cons of each API communication style, and we will see why the next style was even created, right? I hope you're ready. Let's get started. So we'll first start with the fundamental question. What is an API? So API stands for Application Programming Interface. So it is nothing but some kind of a system or some kind of a protocol for two computer systems to contact with each other, right? To communicate with each other. So this is mainly used for exchanging messages between systems, and they need to have some kind of common understanding so that they'll be able to send messages to each other and process them, right? That's the whole idea behind APIs. It could be between a client and a server. It could be between two nodes connected to a single WebSocket server, or it could be between service to service, or it could be between your watch and your phone, anything like that. When two systems are communicating, there needs to be some kind of mechanism for them to talk to each other. So that's the whole idea behind API, Application Programming Interface, right? Now let's talk about why do we need different styles. So the API communication styles have evolved over the years, and their styles have adapted to the needs of those times, basically. So as we move along this video, we'll try to understand the different architectural styles, and then we'll realize that while they were correct in their times for those systems, they had some drawbacks which the next system has tried to solve in sense, and then that had created new problems and which was solved by the other styles, right? So to answer the basic question, why do we need different styles? It's because things change. And no style is perfect. They're just adapting to the times and needs, and then they're just evolving as the needs change. And that's the whole point of software, right? Things change, and our software needs to be able to evolve, and that's the whole idea behind it, right? That's why we need different styles. Now let's go into the 1990s, where SOAP was used. SOAP stands for Simple Object Access Protocol, and it was widely used in the 90s, and it was kind of the de facto standard for exchanging messages between systems, right? So this is how it looked like. So there are clients, and usually there is some big monolith SOAP server, and this is responsible for serving to the client requests, and clients used to send via HTTP some XML messages. So XML is a format with nested structure with very detailed inputs and very detailed response styles, and this was mainly used between clients and servers. And the main use cases were heavy systems and critical systems like banking, healthcare, and so on, where security was very paramount, and they needed very strict protocol to be followed between clients and servers. And that's why they created a system so vast and so stringent that it became a bottleneck in the end. So let's try to see the details of this. So this is how a SOAP request used to look like. So for example, a simple GET request to get the details of a user, let's say of user ID 12345, this whole thing was needed to be sent, right? So there is a SOAP envelope, SOAP header, SOAP body, and then the get user request, then the user ID, and closing tags for all of them, right? And this is how the response would look like. Again an envelope, again a header, again a body, again the get user response tag with the user details, again the data types, and the request body, response body are discussed up ahead, and they're followed to the dot, right? So for a simple exchange of getting user details, so much was required. Now let's look at the pros and cons about this SOAP system. So SOAP was very strictly typed. Both parties had to adhere to the approved protocol, and it was atomic in nature. It was highly supported for transactions, especially you would imagine for banking and healthcare applications. Very contractual. Everybody had to follow what the protocol is. And it has security features like WSDL, so only the secure parties could open the messages and so on. It was very highly reliable. It supported both stateful and stateless services, and this was kind of the de facto standard, right? But there were a few problems. First problem is it was very verbose. Every message was very verbose and heavy. So this was one small example. Imagine if you were a big payload requesting multiple things with filters and so on. This would grow to a large file, and imagine this traveling over the network, and it becomes quite heavy, right? And it was also a steep learning curve for anybody wanting to get into the system, and it was simply an overkill for simple CRUD operations. So it was fine for those systems where everything was monolith, everybody knew everybody else, and they kind of knew what the request and response structures would be like, and everybody just went along with it. But things change, and there was a introduction to mobile phones and wearable devices, and things change. So eventually it looked like an overkill for simple CRUD operations, because the evolution of mobile technology, tablet phones came in, and for doing simple CRUD operations like this, like getting some user details, it was an overkill to build such a huge message and process such a huge response, right? And it was not very suitable for rapid development, because it was very stringent and not very agile, in the sense that it would change so easily, right? And because of this, whoever was carrying the messages, it was really heavy. And the war cry from developers was, we need something simple, please, because the need of the hour was to do simple CRUD operations and very lightweight applications to be built really quickly and roll out to the customers, and it had to be really agile, right? And following SOAP protocol was kind of hindering that process. Now let's go into the 2000s, where REST was introduced. So this is by far the most popular protocol, and you can call it a protocol, you can call it a guideline, but it stands for Representational State Transfer, also known as REST, right? So REST gave us a very simple architecture about how we should go about our APIs, and it used JSON instead of XML. It also supports XML, but mainly this is used with JSON as the format for exchanging messages, and this simplified a lot of things. So this became very lightweight, and it was easy to transfer it over HTTP, and client and server can interact with each other, and server could do the background processing, accumulate all the responses, and send it back to the client. So the use cases were for any web application that needed simple CRUD operations and also some public APIs. It was very easy to roll out APIs using the REST protocol because of these reasons, right? Now let's see some examples about how REST would look like. So this is an example REST request for getting user details, the same example that we have seen before. So for getting the user details of 12345, we just need to say get/users/12345, and the response is a simple JSON, right? So there is no envelope, there is no header, there is no body tag, there are no opening closing tags, and the message is very simple, and the size of the message is also really, really small when compared to SOAP, right? So this resolves some of the bottlenecks that were seen in the SOAP protocol, and because of this, REST became really, really popular. Another reason REST became popular is because of its simplicity to create those endpoints and create some framework, in a sense, to deal with this endpoint. So this framework mainly uses a concept called resource-based design. So you can think of it like some kind of a design thinking pattern, but it deals with giving out APIs based on what actions are being performed on a said resource. So just by looking at the endpoint, we can really tell what it is supposed to be doing, right? So when we look at it, we get /users, right? So just by looking at it, we can say that, hey, it is getting some users, right? And if you look at the next one, it is saying /users/ID. So it is getting some details about this ID, who is a user. So user is our resource, and we're getting some details. So when we talk about post, we are posting a user, which means that we are creating a user. And when we talk about put, we are modifying a user, also known as update user. And when we say delete, we are actually deleting a user. So there are other HTTP methods as well, but it gives a nice little framework for everybody to understand it, and it was really simple to adapt to it, right? And because of this nature, it was really widely adapted, and most of the web these days is using REST, right? Now let's look at the pros and cons about REST. So these are some of the good things about REST protocol, because it is simple, everybody wants to use it, and it follows a simple resource-based design, and you could design for variety of endpoints, even the typical nested structures that we encounter during our architecture designs. Those were also quite simple to be designed in REST, right? And it is widely adopted. And there is also caching support. Because the endpoints are so clear, the browsers were able to cache the responses so that we don't have to hit the same endpoints again and again. And this gave good performance improvement over time, right? And because it uses JSON, this became really human readable. And it supports stateless protocol, which means that every request is independent of the other request. And this was also one of the reasons why REST became popular, because we could just hit 100 requests at a time, and they were all stateless and independent, and we would know that they would not conflict with each other, right? But it was all not rosy. there were some problems with REST as well. So one of the main problems were overfetching and underfetching. So let's have a look at an example for this. So let's say we are getting a blog, right? A blog front end needs to show post title, author name, and author profile picture. Now post is a resource and author is another resource, right? So if we were to get this, so we would get an example like this. So we will call this endpoint post/123 and we would get a JSON response like this. So we get the title, we get the body, we get some comments, and we would also get some author ID. Now we will take this author ID and we will go here to /user/7, which is another resource endpoint, and we will make a new call to fetch the details of the author, and then we will somehow process it in our application layer and get it back, right? So we got the data but fetched a lot that we didn't need. So whenever we are talking about /post/123, we just needed the title of the post, right? And we did not need body, comments, or anything. So these are extra. Similarly, when we made a request to the users, we got email ID, join date, etc. So this was again extra. So the client who needed just title, name, and profile picture was getting something extra, which is some additional data just traveling across the network for no reason at all, and it was not even used on the other side, right? So the client did not have a say about what the server would send, right? So this is an example of an overfetching situation. Now let's take a look at an underfetching example. So the same get post 123, it is returning simply a title. It is not returning any details about the author, which we need for displaying on the UI, author name and profile picture. Now we need to make some other call to get author's details, right? So because of this, there are multiple round trips and extra payloads, and it is an example of underfetching. So in this example, we are not even getting the data we need, and because we need additional data, we need to make some more calls to get the desired data. Ideally, we would want all the data that we need to come in one payload as a response, and that payload should not have any additional data. That would be the ideal scenario, right? But that is not the case with REST and JSON, because the contracts are predefined. The request and response bodies are predefined, and whoever is making the call would get the same style of data, more or less, right? So these are the issues with REST overfetching and underfetching. And because of this, clients had to make multiple round trips, which was again an issue. And it was also difficult to scale in the sense that as needs grow, we need to change the response style of the JSON. And for every change, we need to be making sure that we are doing backward compatibility so that the previous users or whoever we were supporting earlier, they would not be affected. So it was slightly tricky to change the response. Adding was easy, but removing or changing stuff would be very difficult. It was not really super agile that it would just accept any kind of change. It needed some thinking and careful planning to make sure that things scale over time, right? And also, evolving needs for mobile, tab, web variables came in, which was an issue for REST because so for a mobile, let's say we just need to show post title, author name, and profile picture, but in the web, for the same endpoint, we need to show different things, maybe a detailed description, a snippet, or TLDR, or something like that. And for variables, we just need to show the title, let's say. And everybody is calling the same endpoint, and they're getting the same data, which they don't need. Again, the same overfetching, underfetching issue concepts were a real issue. So the main issue was this one. Server is deciding what to send, and client had no say. That was the whole big issue when it comes to REST endpoints. So in this case, the devs are saying, why should I call 5 REST endpoints to load a single page, right? That was the issue. So to solve this, there was GraphQL. Let's go into 2015 now, where Facebook introduced GraphQL. So GraphQL, instead of thinking of it from the server side, they started thinking of it from the client side, and they saw that we don't need so many endpoints. We can still do the resource-based design, which was really good of REST. And instead of giving multiple endpoints for different type of operations, we would just give single endpoint and let client choose whatever they want to do with the data. It made sense, and let's see how this goes like. So let's say there are a couple of clients. One is a web client like this, and let's say there is another client, mobile, and both of them want to talk to the GraphQL server. Okay, so this server is serving one endpoint /GraphQL or something, and in this, clients can request whatever they need. For this, I need ABC. For this, I need XYZ. right? And the server is able to do the internal computations depending on the client's request body, and it is able to generate those responses as needed for different types of clients. And there is a whole engine running here called the GraphQL engine, which takes care of this transpiling or transformation, whatever you want to call it, and serving everything in a single endpoint. So this made things really simple, and it solved the problem of overfetching and underfetching, which was the case with REST, right? And because of this, clients ask what they need, server resolves it, right? Resolve being the keyword here, because GraphQL works internally using resolvers. So there are query resolvers, there are mutation resolvers. So query resolvers fetch the data and take the needs of the clients and transform it to the data format that clients need. And mutation resolvers actually take the inputs from the clients and change the data on the backend, right? So these are resolvers. And the main use cases for GraphQL are when there are multiple client modes. So for example, we are serving multiple types of clients like web, mobile, wearables, and so on. And the data requirements are quite complex from multiple sources. That's when we can go for resource-based design and GraphQL endpoint. One of the main examples can be real-time dashboards, where clients can cherry pick what metric they want to see, and we will just serve those metric details and show them in real time, right? So these are the use cases for GraphQL. So let's have a look at an example. So we'll go with the same example. The client needs post title, author, and profile picture. So this uses the concept of graph, where one thing is connected to the other using edges, and the edges can go as deep as they need depending on the graph's depth, right? So in this case, there is one level depth, post and author. So client can request is like this. So I need a post with ID 123, give me a title and give me also an author, and within author give me a name and give me a profile pic, right? So this is how clients can make a request with a nested structure. And GraphQL response would be something like this. Hey, here is your response. The title is this and the author is Jane with some URL, right? Very simple. It still uses JSON, which is human readable. That is also an advantage. And this is how GraphQL works. Let's see the pros and cons of GraphQL now. So there is no underfetching, there is no overfetching. Front end gets really flexible. API evolution is also easy because we could just keep adding depth to our graph structure and clients would just be able to use it. Because of this, there are reduced calls to the server, and the schema is strongly typed, which is also a good advantage because clients can always know what type of data is coming back from the response. And this is still JSON, which is really good. And it also supports subscriptions using WebSockets, which means that clients can subscribe to certain event, and whenever that event happens, they get the response back, right? Similar to chat applications, right? So these were all the good things about GraphQL. Now let's look at some of the problems. So caching is complex because we don't know what the client is requesting and it's a single endpoint. And because of that, caching becomes a little trickier. And there were also some performance issues as schema grows. And especially there's a problem called n+1 problem. Let's try to understand this. So let's say we are querying multiple posts now, and this is expected to return some kind of an array with multiple posts, right? Post 1, post 2, and so on, right? Let's say there are 10 posts like that. And for each of the posts, we need to get the author details, right? So internally what GraphQL is doing is, it does not know how many posts will come. It does not know for how many people we need author details. So first it fetches 10 posts, blog posts, and for each post it makes a call to get author of post 1, author of post 2, author of post 3, and so on up to author of post 10. So if there are 10 posts, it is making 10 different calls. If there are n posts, it is making n different calls, and this is the n+1th call for getting the post, right? So that is the n+1 problem. So if you'd like to know more about it, I'll leave some documentation in the description below. You can check it out. So this is mainly solved by using data loader batching, which is supported in GraphQL. So because of this batching, we just take details of all the 10 posts, the author details, and then send one request over the network for getting all those requests and reverse engineer them into the post and then send it back to the client, right? And another issue is it requires a dedicated GraphQL engine always up and running to make this all magic happening. So these are some of the problems with GraphQL. And now the devs are saying, okay, but what if there is no client? Can we do better than JSON? Right? So we came from XML to JSON and we saw that there's a big improvement in terms of size and simplicity, and it is also human readable, right? But what if we don't need it to be human readable? Can we compromise for readability and make responses faster? And that is a question we are asking with the next one. So now we are going into 2016, where we are seeing the evolution of gRPC. So in 2016, Google released this gRPC protocol, and RPC stands for Remote Procedure Call. So as the name suggests, clients are making a procedure call on the remote server as if they're calling it in their local machine, right? That's the idea behind RPC. And Google made it very, very generic. So this was initially associated with Google, but over time it evolved into multiple different languages, and now it's just generic or general purpose remote procedure call, right? So this is how it looks like. So there's a gRPC server. It's running on any of the programming languages. In this case, it is running on C++ service. And there are a couple of clients. One is running on Ruby, another is running on Android or Java. And they're having their respective gRPC stubs. So they're making a request and they're getting a response. And this stub is responsible for converting the proto request and proto response to the language that is being used. So internally, there is a proto file being used, which is nothing but protocol buffer, and this is used in binary format, and any type of programming language can use this. So Google has taken it upon themselves to create the landscape for different programming languages to support .proto files, and if the proto file needs to be converted to a C++ service, it can do that, and similarly for any other programming language, right? So basically, if you're requesting for, let's say, JavaScript, the proto file, when converted to a JavaScript, it will give out the different classes, methods, and objects that are required in the syntax that JavaScript needs. And similarly for other programming languages, right? So this is how gRPC communication looks like. So it uses proto files using protocol buffers, and it is binary format, which means it is really, really small, almost half the size of typical JSON, right? And because it is binary, it is not human readable, right? So this is how gRPC works. So the main use cases for gRPC were to build service to service communication and make it really, really performant, especially in systems where multiple programming languages were used. Something like this. Here we see Android, Ruby, and C++. So these are called as polyglot systems. So imagine there are multiple services talking to each other, and let's say there is no need for human readability, right? So services can communicate with each other at rapid speeds and minimum network calls, right? So that's how gRPC works. Let's see the good and bad about gRPC. So it is extremely fast, it is very compact, it is strongly typed. Every proto file needs to be clearly defined and to be converted into the respective programming languages. And this is the main advantage of using gRPC. It uses protocol buffers and serialization. Serialization is nothing but converting things to binary and backwards to the respective language. And because of this, it is very language agnostic. Because gRPC is supported in multiple languages, anybody can pick up any language and start using it without any issues, right? But the problem is not human readable, low browser support, and learning curve is high, because this involves learning what are protofiles, what is gRPC, how do we make calls between systems, and how to debug binary format stuff, how do we do serialization, deserialization, and so on. All these stuff need to be learned, and because of all these, learning curve is slightly higher. So as we have seen, there is no architectural style that is perfect. So they all have their needs, they all have their pros and cons, and it is up to us to decide which one to use when we are actually building a system from scratch, or when we are adding stuff to our existing architecture. We need to make a decision whether we want to go with REST or GraphQL or gRPC, right? So how do we choose it? So here is a simple decision tree to make our life easier. So we start by asking who is consuming our API. And if the answer is front-end mobile clients, the next question we ask is, do we need flexible data fetching? If yes, then use GraphQL. Otherwise, go for simple REST endpoints. If the client is internal microservices, so there are no humans involved, we can go with gRPC, where high performance and low latency is required, right? And if you need streaming go for gRPC. And if you need simple, stable service communication, go for REST or gRPC. And if you want to expose the same APIs to both internal and external services, you can go with REST, or you can also go with GraphQL with a dedicated gateway, right? We spoke about gateways and why they work and how they function in the previous videos. So definitely check it out if you have any doubts on that front, right? So that's all I had for this video, guys. Thank you so much for watching. I will definitely leave some documentation for you to check out for all these different topics. So make sure to check out, and if you have any doubts, don't hesitate to put them in the comment below. And please leave a like if you found this helpful. Do subscribe if you haven't done already so that you don't miss out on any future videos. Thank you so much for watching. I will see you in the next one. Cheers.